probability that Janice sees a kingfisher on any particular day is 0.3. She notes the number x of days in a week, so that's going to be 7 days on which she sees a kingfisher. State one necessary condition for x to have a binomial distribution. Now, in these questions, you can't just learn like independent and the probability stays the same. You must give context related to the question. So you can either write the probability of seeing a kingfisher is the same each day. Now, I know it kind of says that on any particular day is 0.3, but we don't know that's kind of an average taken over time, over months, and that is what it is, typically 30%, because it might vary from winter to summer, for example. So in our binomial distribution, we have to always have it to be the same. Second reason, you only have to give one, but I'm going through answers here, so I'm going to give you a second reason. So, so the observation or the observations are independent of one another. Now, I think that's fine. I'm just going to quickly skip to the mark scheme to show you that. So they say, oh, sorry, it's not quite, I can't quite see it from here. Here we go. So they say seeing a kingfisher on one day is independent of the other days. Now, I feel like I've said that in fine. Have I given enough context? Maybe not, because it doesn't accept probability of seeing a kingfisher is independent. So have I done enough? I'm not sure. Maybe seeing a kingfisher on one day is independent of other days. I don't know. I feel like mine's fine, but maybe just mentioning the word kingfisher would have been better. So perhaps go with that instead. On to part two. So now we're assuming that B has a binomial distribution. The first thing I do before I even look at the question is to write this binomial distribution down. X follows a binomial distribution with 7 trials because it was over the course of a week, and probability of success of seeing a kingfisher is 0.3. That sets everything up. We've got N and we've got P. And then we want to calculate the probability that X is equal to 2, exactly 2 days. I'm going to show you 2 ways to do this. There's the way that you put it in your calculator and you don't have to show any understanding whatsoever of what is actually going on. And there's the way that actually explains what is happening. So for the quick way, and obviously you want to learn this way, but it's also important to learn what it's doing. Go to distribution, and then it's not cumulative, it's PD, just to find one probability. And we only actually want to find one value, so I'm going to go to variable and put x in. So x is actually 2, that's the number of successes I'm interested in. N is 7, and P is 0.3. Press equals again, 0.3176. So 0.318. Right, here's the second method showing understanding. And by the way, this can be asked on A level, so it's not just a case of forget about understanding it. Let's just learn how to apply it in the calculator. No, also look at the understanding. So for me to get 2 successes, one way I could get 2 successes would be to have success, success, and then 5 failures. And the probability of getting along a tree diagram, success, success, I would times them together. So it would be 0.3 squared. And then if I have 5 failures in a row, I would then times by 0.7, because if success is 0.3, failure is 1 minus that to the power of 5. And then we just have to think about the different ways that you can arrange S, S, F, 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 F. We're actually arranging 7 things, and there are 7 factorial ways of arranging 7 things. Okay, I'm assuming you've done this before, like, assuming you've seen this when you're covering this topic, because I'm not going to go into lots of detail on it. However, these two are the same, so I'm gonna kind of double count, because when I swap these two around, it still looks the same. So I have to divide. Actually, we say we divide by 2 factorial because 2 are repeated. And then when I swap these ones around, I will also get repeated ones, and actually I need to divide by 5 factorial. So, and this is sometimes written, by the way, as 7c2. Same thing. Sometimes also written as 7,2 like that. Now, I'm not going to do this bit without a calculator. You can do, but I'm already going into quite a lot of depth on this question. So then I would do 7. Here's the C button, C2 times 0.3 squared times 0.7 to the 5, which gives us that same answer. So this is explaining why it works. And this formula in the formula book is a generalization of that. So if x follows a binomial distribution with n trials and probability of success is p, then the probability that x is equal to x is this permutation formula. This is actually ncx. All the different ways we can arrange the x successes and the n minus x failures. And then we times, imagine we're going along one branch of the tree diagram, we just times by the probability of success x times as we go along, and then the probability of failure n minus x times. I'll go into more detail on this on other videos. I just wanted to talk about it here. Okay, I feel like I've talked about that quite a lot. This is a 1-mark question, but please make sure you understand what is actually going on. Okay, on to part 3 of this question. Each week, Janice notes the number of days on which she sees a kingfisher. So we're not just looking at a week now, we're looking over the course of a few weeks. Find the probability that Janice sees a kingfisher on exactly 2 days in a week during at least 4 of 6 randomly chosen weeks. So actually, this is a binomial distribution within a binomial distribution. Let y be the number of times that Janice sees a kingfisher 2 days in a week. And we're looking over 6 weeks. I'm not going to write any more, but I'm going to like any more words, but I'm going to say that y is therefore going to follow a binomial distribution. That's going to be 6, because there's 6 weeks I'm looking at, and the probability of success is this answer we had above, 0.3176. Now, actually, I wouldn't just work to 3 significant figures here. I'd work to a few more. So I'm actually going to include a 5. Do I need a 2, 3 in there as well? I think that's the decimal terminates them, but I've got enough, I think. Let's do it. And we want to know the probability that y is greater or equal to 4 during at least 4 of 6. So if I draw this on a number line, actually I've got 4 here, and then I've got 5 and 6. So one way of doing this is to just find the probability when y is 4, add it to 5, and add it to 6. But there's another function you can use on your calculator that will deal with it more easily. Your calculator has the ability to look up less than or equal to. So actually, this probability is going to be 1 minus the probability that y is less than or equal to 3. Because 1 is the whole thing. And then what is left over is actually this bit here. 3, 2, 1, and 0. So I take 1 and I subtract this bit, and that will leave me the probability that x is greater or equal to 4. And I would just use a calculator for this. This is where the calculator really comes into its own. But be aware you could do it by, adding those probabilities on. Distribution. This time it's binomial CD. Still going to use variable, and now I'm looking at x is less than or equal to 3. So that's the one I put in. You've got to make it less than or equal to. If you start putting in 4 into your calculator, it's going to be less than or equal to 4. That's not actually going to help. N is equal to 6, and P is this long decimal. Okay, I don't need that many, but I've done it. And then we get 0.91462. So remember, it's 1 minus that. So I'm pretty sure that stores it in the answer button. So if I go back to menu 1, I do 1 minus answer, and we get 0.08537. And at this point, I rounded to 3 significant figures. Okay, solid binomial question. Well done.